In my last video, I talked about power functions and how we can use transformations to graph them. So our power functions have these nice kind of shapes, either the U sort of shape for even degree power functions, and then the elongated S shape for odd degree polynomials power functions. The issue, though, is that most polynomials actually don't have this format with a single x being raised to an even or odd power. Most polynomial functions, oops, too far, actually look like this for their graphs. They have these kind of twisty, turny looking graphs, and they definitely don't look like those two power functions that we just saw. And the reason why our polynomial functions look this way on their graphs is because we do have multiple terms with different powers of x. So those different powers of x, in a sense, can battle each other out and create these kind of interesting curvy-like behaviors on the polynomial function. So how do we graph these? They definitely have very different and interesting behaviors that we want to capture. So we're going to be looking at some very key aspects of behavior that are going to assist us in graphing. So one thing that all these polynomial graphs have in common is they have x-intercepts, and usually interesting behavior is going to happen very closely around these x-intercepts. So finding the x-intercepts is going to be a key thing that we do in our graphing process. So x-intercepts is a key aspect of behavior. Another key aspect of behavior that we can see here is on those x-intercepts, they kind of act different ways. Sometimes my graph goes through the x-intercept. Sometimes it kind of bounces off and doesn't really cross through the x-axis. We kind of have these different sort of behaviors occurring at the x-intercepts. And so that's going to be a concept that we call the multiplicity of the x-intercept, and that'll help us figure out the sort of behavior that's happening if we're crossing through the x-axis, or if it's kind of that we call a touch or tangent behavior at that x-intercept. Another key aspect of behavior that is usually pretty obvious in all these is that we do have our graph kind of twisting and turning and going from increasing to decreasing or decreasing to increasing. We have talked about those in the past as local maximum and minimum points. And for the purpose of our polynomials, we call those turning points, because that's where our graph, in a sense, is turning. It's going one behavior and then kind of changing its mind and going a different direction. So we call those turning points. In the past, we've called those local maximums and local minimums. And the last key aspect of behavior that's actually really, really important on these graphs is what happens to the ends. So we don't want to have to draw this massive graph, and luckily we don't have to. That as our values kind of get large, either negatively or positively on my x values, that our graph becomes a lot less unpredictable and actually very predictable. So we can kind of see that the what we call the end behavior of our graph is very predictable, right? That although it twists and turns in some parts of the graph, that eventually the ends are going to be very predictable and act in a very predictable way. So those will be the aspects of behavior that we're going to look at, and what we'll see is by looking at those four aspects of behavior, our x-intercepts with their multiplicity, the end behavior of the graph, and the turning points, that we can generate very good graphs of these polynomial functions. Now, before we get started on all that, there is some language and kind of definitional things that we want to cover because they will use different terminologies, and we want to make sure that we understand these terms. So you may hear, we've heard of x-intercepts before. Maybe you've heard of zeros. We've definitely talked about factors and solutions. But these four phrases are really getting at the same thing, and we use them kind of interchangeably, especially in this section. And we want to make sure that we understand that these are discussing the same idea, but they're also addressing it in kind of subtle and different ways. So if I have some number r, and it's a real zero, so it's a real number, and we say it's a zero of the polynomial, that's saying that when I input that r value, as my input variable into my function, that the output that I get is 0. And graphically, we've seen this in the past, right? What that's saying is at that particular r value, my output, or y, is 0. And we called those in the past x-intercepts. So I would say this r number, whatever it is, I could call it a 0. It is also by definition an x-intercept of our graph. And when we were dealing with quadratics, we factored quadratics, right, to solve them. And so you would, get x equals r, say, if I have multiple factors here, we would set each factor equal to 0 and then solve. And so we also consider it a factor of our polynomial, because quadratics and polynomials, you need to factor them in order to find all the different solutions. That's the only way to actually solve them, since they're not linear. So we might say that x minus r is a factor of our polynomial. And we may also call it a solution, that r is a solution in the sense that it will create an output of 0. So those 4 terms are really getting at the same idea. What is x, or the x, I guess you would say, that generates an output or solution of 0 on our function? And so we kind of use those terms interchangeably, but they mean the same. Although they mean the same thing, we're addressing them in different contexts, right? So I'm calling it a 0 and a solution kind of in the same way that it yields an output of 0. It would be a factor if I factored my polynomial function, and if I looked at the graph, it would be an x-intercept on my graph. All right, so the first step when we're given a polynomial is to find those zeros, find the x-intercepts on our graph. And so those would occur because they're factors. X, we say x minus r, right? Because r is the x-intercept or solution value. So x minus that number would be a factor. And sometimes those factors are repeated multiple times. And so say, I repeated a certain number of times, we see that as a power. And that power is what we call the multiplicity of the root, right? Essentially, it's how many times that solution or x-intercept is occurring within our polynomial equation. So here I have an example, and thankfully it's already factored for us. And that's actually a common way of writing our polynomial functions because they are not the easiest things to factor. So if we can be given our polynomial function in the factored form, it really helps. We don't have to go through that work of factoring it. Because as we learned when we were learning all of our factoring methods, that when your power gets large enough for your variable, that it gets very difficult to factor them with standard factoring rules. So we'll be dealing primarily with either polynomials in this factored form, or if it does require us to factor it, it'll be following one of our factoring rules that we've seen in the past. So this polynomial is already factored. So to find the zeros, those occur when y is 0. So I'm going to set this equation equal to 0. And the point of factoring is so that then we can claim that each of these factors is equal to 0. Now before I do that, I might get a little distracted by this 5 out in front. So the 5 actually isn't contributing to one of our factors. It's just a multiplier on the outside. It's just a constant multiplier. So unless there's an x on it, it's not going to be one of our factors. So if it's kind of distracting, what you could go ahead and do is divide both sides by that 5. So it would get rid of it on the right side, and then 0 divided by 5 is still 0. So I still get the same x values for my x-intercept or zeros. That 5 doesn't really do anything for that. All that 5 would do in terms of our graph is affect the shape a little bit and maybe the y values that we get, because your y values, once you calculate them, would get multiplied by 5. But for our purposes, for the zeros, it doesn't do anything. So I'm going to go ahead and take each of these factors and set them equal to 0 and solve. So I get 1, 0 is at x equals 2. Now the next 0 has a power of 2 on it. And I could write, x plus 3 in parentheses squared, and then square root both sides. But that's still going to get me x plus 3 equals 0 because the square root of 0 is 0. So we can kind of ignore any powers if they occur on our zeros because they don't affect the solution that we get. So I would say that one has just the repeated x value of -3. And we'll talk about the multiplicity here in a second and how that affects those repeated values. Same sort of situation on this x minus 2. I could leave the power of 4 and then complete the fourth root on each side, but that's unnecessary. You still get, the x minus 1/2 equals 0. And then we can add 1/2 on each side and get x equals 1/2. So those are my zeros. Now we want to talk about their multiplicities. So the multiplicity is referring to how many times that 0 is repeated as a factor. So for the x minus 2, we only see it occurring once, and in fact it kind of does have an implied power of 1 if we don't see any powers there. So we would say it has a multiplicity of 1. The x minus 3, 0, when we had it in the factored form, had a power of 3 on it. So we would say that it has a multiplicity of 3. Had a 2, pardon. So it had a power of 2. So we would say that it occurs twice in our factored list. And so we say it has a multiplicity of 2. And then the 1/2 came from the factor x minus 1/2. It had a power of 4. So it would have a multiplicity of 4. So why do we bother finding the multiplicity? That's because it's going to dictate the behavior that occurs at that particular 0. So for that 0 value, which is an x-intercept on our graph, if your multiplicity is even, right? In other words, our factor happens an even number of times, then that's going to be what we call that touch behavior. And that behavior, when we saw it on our other graphs, that's where at that particular x-intercept, my graph doesn't actually cross through the x-axis. It kind of approaches the x-axis, it takes on the value at that x-intercept, and then goes back to where it came from. So it could be coming, say, from the top, positive values of y. It could be coming from the negative values of y. The key part is, it's essentially a turning point there at that x-intercept. If my multiplicity is odd, then that's what we call that cross behavior. And so a cross behavior is where my graph will actually cross through the x-axis at that point. So it might come from the positive y values and crossing through to get negative values, or it could go the other direction, coming from negative y values, crossing through, and then obtaining positive y values. So either way, we're going to cross through the x-axis. And so it's, in a sense, a very different sort of behavior than the touch behavior that we've been seeing. So if we look at that same factored polynomial equation that we were working with previously, we found our zeros. So the first one was a 0 of 2. It had a multiplicity of 1, which is odd, right? 1 is not an even number, all right? It's not a multiple of 2, so it's considered odd. And so that would mean that at that particular location, it's going to have that same odd multiplicity behavior. We would consider this, a cross type behavior at that x-intercept. The next 0 or x-intercept that we found was at -3, and it had a multiplicity of 2, which is even. So that means we're going to have that touch. Sometimes it's called a tangent behavior too. So sometimes this is also referred to as tangent because it's tangent to the x-axis. And then the last 0, which was x equals 1/2, had a multiplicity of 4, and that would also be a touch type behavior. So now I know where my x-intercepts are, and I know the type of behavior in terms of how that x-intercept is going to act, whether it crosses through or just barely touches the x-axis. Turning points, there is a way to know how many of those turning points, those local maximums and minimums there are on our graph. So we can determine that by looking at the degree, the highest power that our x obtains in our polynomial. So if your polynomial function has some degree, which we call it n, then it would have at most one less, n minus 1 turning points. So just as an example, say I had a say 4th degree polynomial, right? The highest power of x was 4. Then that means at most I would have one less. I would have 4 take away 1, I would have 3 turning points. And we say at most because it could be fewer, right? Depending upon the terms in our polynomial and whether they're positive or negative or what their coefficients are, it could be fewer. But we definitely know the maximum amount that we could have at most 3 of those local maximums or minimums or turning points. And it also kind of works in reverse. If I had a graph given to me, right, say here's my polynomial, I could count the number of turning points. This one has 1, 2, 3, 4 turning points. And that would tell me the least degree polynomial that would generate that. So if I add 1 to this, right, the lowest degree polynomial that could create this graph is a 5th degree. And again, it could be more. It could be 6th degree, 7th degree, 8th degree, but it can also help us understand what the minimum has to be as well. So if I go back and look at that example that we looked at for x-intercepts, the issue is just the fact that it's in the factored form. So the factored form was great for finding our zeros. It allowed us to very easily calculate the zeros since it was factored. However, it's not telling me what my leading term is. And so I could go ahead and multiply this whole thing out and make it look like our standard polynomial, where you have the highest power of x, then the next highest power, and so on. But that's a lot of multiplication. I'd have to multiply this x minus 1/2 by itself 4 times, and I'd also have to multiply x plus 3 by itself twice, and multiply those together, and then also multiply x minus 2 and multiply by 5. That is a lot of work, and really we don't need to do it. All that we're interested in determining is our degree, which is the highest power term of x. I don't care or even need all the lower power values of x. So what we can do to kind of get around doing all this insane multiplication is just anticipate what the highest power of x would be for each of these factors once we take into account the multiplicity. So if I did multiply out x minus 1/2 by itself 4 times, right? X minus 1/2 times x minus 1/2 times x minus 1/2 times x minus 1/2. This would be a massive multiplication problem, but the highest power term for each of those factors that I could potentially get for x is just x to the first. And those would eventually multiply by by each other. So I'd have x times x times x times x, which is x to the 4th. So kind of ignoring all the other terms that come out of it, the highest power of x that I could ever achieve by multiplying these guys together 4 times would be x to the 4th. So I'm just going to keep track of the highest degree power that comes out. I could do the same thing for x plus 3 if I keep track of the highest power of x that would result from my multiplication. This is a foiling problem. We know the highest value we could get for x for each of those is x times x, which is x squared. So that would be the highest powered of x term that comes from there. The next one is linear, so the most that would come out of x minus 2 is just an x. And the 5 doesn't have an x, but I actually want to keep track of that because the 5 is going to help us when we're looking at some of our end behavior later, because we need to know the leading coefficient. So what would be the leading term here? Well, it would be all these things multiplied. So it'd be 5 times the x times ex squared times x to the fourth. So when it's all said and done, that's 5x, and the power would be 4 plus 2 plus 1, which is 2 to the 7th. So the degree of this polynomial is 7. Now I can find out the number of turning points. So I could have at most 1 less than my degree. So 7 take away 1 means I have at most 6 of those turning points. Okay, and last but not least, we're going to look at the end behavior. What's going to happen to the tail ends of my graph when I have very large negative x inputs or very large positive x inputs? You know, what direction is my graph going? So here we need to look at the leading term. The leading term is going to dictate our behavior. So we actually found that in the previous example. We found that the leading term would be 5x to the 7th on this. So what is that telling me? Well, this kind of goes back to when we discussed those power functions, that our behavior kind of falls into two categories, that I could have kind of the even, this is for the degree, I could have even degree behavior, which is our parabola shape. So it'd be kind of like a U shape. And I could also have odd behavior from the degree, which is that kind of cubic S-looking shape. Now both of those happen when our leading coefficient is positive. So when the leading coefficient is positive, that's the way our graphs would be oriented. However, I could have my leading coefficient be negative, and that negative is going to create a reflection over the x-axis. So we've seen that with parabolas, right? When we do like negative 1x squared, that makes it open down. And the cubic graph, that kind of S shape, would do the same thing. It would get reflected and in a sense be flipped, right, in the behavior. So here I remember these 4 cases essentially based off of our typical graphs that we had in the past. So this is like the positive 1x squared and negative 1x squared. And these other 2 graphs are like positive 1x cubed and negative 1x cubed. Now before we jump to the conclusion that that's exactly what the graph looks like, that's really only what the end behavior is going to be doing. That the sections in the middle, we don't really know how many turning points there are, how many x-intercepts that we have, so we usually kind of ignore the center sections, that we don't know what's happening there. All that we really do know is the tail ends and what the tail ends are doing. So if I want to decide which of those 4 possibilities my polynomial is going to fall under, we would see, you know, is the degree even or odd? Here my degree is 7, which is an odd number. So it'd be definitely one of those kind of S shapes. And the leading coefficient is positive. So it's going to be this case here. And how we describe that, we can kind of describe it 2 ways. A common way is to discuss it in terms of what x is doing when it gets very large negative or very large positive numbers. So if x is approaching essentially what we call negative infinity, right? This kind of left side of the graph. So x is getting very large in the negative values, that my outputs, the y's, are also getting very large in the negative value. So because we're dealing with functions, we don't say y, we say f of x, and we'd say it approaches negative infinity. So that would be how we would describe this behavior here on the left. That's symbolically. We can also kind of say it in words by saying that it falls, that the graph will fall on the left. So that's how we could describe it as well. Then on the right side, it's increasing. So when x is getting very large positive values or approaching positive infinity, then my y values are also becoming very large positive values. So f of x would approach positive infinity. And again, that's the symbolic way of writing it. How we would say that in words is that it rises on the right. So those would be the two ways that we could describe the behavior. We could describe it symbolically with what, x and f of x is approaching either positive or negative infinity, or we can say it in words as either falling or rising on the left side or the right side of the graph. Okay, so let's pull all of that together. We found all the key aspects of behavior for that example. So let's go ahead and graph it. What we can see is by looking at those 4 aspects of behavior, we can actually generate a very good graph of this polynomial function. So we found our zeros. We had a 0 when x was 2, -3, and 1/2. And because of the nature of our polynomial function, scaling is very important. That using a scale of 1 may not be appropriate. And in fact here, especially because I have the 1/2 and because my x-intercept values are not very large, I don't want every tick mark to count by 1. I'm actually going to let every other tick mark count as a 1, so I can kind of get a more zoomed in look on my graph. And that's fairly common, that when our values of x get large, so does the y values. And so we don't really need very large values of x typically to capture the key aspects of behavior. So let's graph those x-intercepts to start. So I have x equals 2. And we know that's going to be cross behavior. So I'm going to put a little c here to remind myself that's a cross type behavior. At -3, I have an x-intercept as well, with a touch or tangent type behavior. And at 1/2, positive 1/2, we have an x-intercept also with the touch or tangent behavior. Now I know the maximum number of turning points, so at most I would have 6 places where I have a local max or min. I don't know where that is yet though. We don't have enough information to kind of graph this guy. And then the end behavior is also very crucial. So x-intercepts and what's happening at those x-intercepts is very important. And the end behavior is also very important. So we know that on this left side, it's going to fall. So I know it's going to fall on the left here, which means it has to, and I can kind of start getting a sense of my graph, right? It has to come up then to touch my x-axis at -3. Since it is a touch behavior, it's going to come back down. And at some point, it's going to have to turn around. So we're definitely going to have a turning point to come up and touch again at 1/2. So it's going to turn around again and have to turn again to come back up and cross through at 2, and then have the final end behavior of rising on the right. So to get a very, I have a good sense of the sketch here, but I want to be a little bit more accurate in terms of where my graph is going to turn around. So really, not so much the values outside the x-intercepts, but really the values in between the x-intercepts is what I'm interested in. So I could go ahead and kind of make myself a table of values or calculate maybe the whole numbered values between my x-intercepts, between this -3 and +2. So I'm going to use a calculator to aid me in that because we do have a rather complex function that we're working with. And we can, if we're very careful, we can type it in just like you see it here. So let me calculate the value at -2. So I'm going to do 5, kind of like we see it there with parentheses. This would be -2. Oops, let me make him negative. -2, close parentheses, times -2 added to 3, and we will square that. And then -2 minus, and for the 1/2, I'll just go ahead and do 0.5, just to make typing this out a little bit easier. So 1/2 is the same as 0.5 raised to the 4th power. And I get a massively negative number. So we know it's going to drop very, very drastically for that value that we're seeing. So let me go ahead and calculate -1 and see if it continues to drop. So I'm going to take my previous result here And we'll change our x value now to a -1. So before I start graphing stuff, I just want to know how far I have to go on my scale here. And polynomials can get very, very large y values. And so I want to make sure that I pick an appropriate scale. Okay, so it's not quite as large. Yeah, so I definitely want to hit almost to -800 to capture that lowest behavior. So what would be a good scale here? Let's make every other tick mark, say 200. So it'd be 200, oops, negative, -400, -600, -800, -1000, -1200. Okay, and you might have picked a different scale as well. The key part is we want to capture those really large or really small numbers as we're getting them for y. Okay. And let me pull up my calculator. So at -2, we were just below -800. So I'll put a dot there. And at -1, I was a little bit past -300. Okay. We can also calculate our remaining kind of whole numbered values. I can see where I am at 0. I can also see where I am at 1. And if you have a calculator that allows you to go back and type in your results, kind of like I'm doing here, it makes it definitely a lot faster to calculate these. You could also write them out and calculate them by hand. Okay. So at 0, I'm actually not that large at all. I'm at about -5, a little bit past -5. So we barely see that. Very, very close to 0. And then at 1, let's find the value at 1. So at 1, I'm at -5. So again, not very large at all. Okay, and that should be more than enough to give us a very nice graph. So I know on the left side here that my graph is going to be falling. It has to come up to touch that first x-intercept. So it's just barely going to touch and drop down all the way to that -700 number. It's going to come back up to 300 to come up and touch again at the 1/2. It's going to turn around just barely, you know, and here if I wanted to find maybe the value at 1.5 to see how low it goes, it probably can't go that low if it's going to come back up to cross at 2 though. And then continue on and be rising on the right. So there we captured that very complex looking polynomial function by analyzing the behavior at our zeros, so finding the x-intercepts and knowing the type of behavior, by looking at the end behavior, and we can verify that we haven't misgraphed this by looking at the turning points. So I actually had 1, 2, 3, 4 turning points, which is under the maximum of 6. And we just found some additional point values in between our x-intercepts to get a sense of where those kind of turning point values are going to be.